All right, so let's take a look at Chapter 18 for exam number 7, which will be next Tuesday. No, next Thursday. This coming Thursday. Today's Tuesday. So it'll be Thursday, the 23rd. And I'll see if, like I always do, first I'll open the floor to questions. And then if there are no questions, then we'll run through the review document. And that may spark some questions. All right. Okay. Guess it's not at work. She's outdoors. I see clouds and a power line. Oh, well. So let's look at, if there are no questions, we'll take a look at number 1 in the review document. And it's a word problem. And the reaction is between sodium bromide and chlorine gas. Sodium bromide and chlorine gas, which is diatomic. And it produces sodium chloride and bromine. Sodium chloride and bromine, which is also diatomic. Now, just out of curiosity, we said this one was a gas. What should bromine be at standard temperature and pressure? It's a liquid. That's not relevant to the problem, though. The question is, what are the appropriate half reactions? The oxidation reaction and the reduction reaction. So one of the first things I would do is determine what's the oxidation state on every element in the reaction. And then balance the equation also. So remember, oxidation states on elements in their standard states are 0. So those are the easy ones. The oxidation state on ionic compounds is the charge on the ion. So this would be -1, this would be +1. This would be -1, and this would be +1. And so we have all our oxidation states. Now we need to balance the equation. Now the question is, do we need to balance the equation by half reactions? We eventually need to get to half reactions, but we might be able to balance the equation in a molecular state without using the half reactions. And it looks to me like we need 2 chlorines over here and 2 bromines over there. So that gives you 2 chlorines, 2 bromines, and 2 sodiums. And that's balanced. So we didn't have to do half reactions to balance the equation. You can if you want, but it needs to be balanced before we can answer the question. Okay, so who's reduced and who's oxidized? Let's see. The answers are in the order of oxidation reduction. So we'll do oxidation here and reduction here. So who's getting oxidized? Let's see. Oil rig. Oxidation is lost. So who lost electrons? It looks to me like bromine lost 1 electron per atom. It went from -1 to 0. So it lost 1 electron. So our half reaction would have bromine here and the bromide ion, and then bromine here, right, at 0. And we've got 2 bromines. There we go. So if we've got 1 electron per atom, that means 2 electrons had to be lost in the process. Okay? That's our oxidation. Reduction would be whatever's left. Notice that sodium doesn't change. Sodium is a spectator. So it doesn't even enter into the oxidation reduction reactions. So we've got bromine, so chlorine must be the other one. At zero oxidation state, it went to -1. So that means the electrons have to be reactants. We have to add an electron per chlorine, and if we've got 2 chlorines, here, 2, then we need 2 electrons. And those are our oxidation reduction reactions. Let's see which one that is. Looks like B. Hey, you want to help? Just sit down. Sit down and watch. Just watch. Okay, is that all right with everybody? Here, you're going to have to move. All right, that was number 1. Let's see, number 2, is that introduce? Yes, 2. Better do number 2. All right, we're given the reaction is between ammonium metavanadate and sulfur dioxide in acidic solution. So the temptation is to balance the entire equation by the method. But to answer the question, which is, well, let's write this up here first. We've got a coefficient of that for the vanadate, which tells me that ammonium is a spectator. And Y times sulfur dioxide yields what? Another X times VO2 plus and Y times SO4 minus. So according to algebra, if you give a variable the same symbol, whenever one solution is one value, the other one has to be the same value. So that tells me that these 2 x's have to be the same value, these 2 y's have to be the same value. And the ratio is the question. What's the ratio of x to y? All right. So I might have to redraw that because I'm gonna use a method that's quicker than the half reaction method. Let me do that again. Put the 2 up here. Then I'll put the rest of the equation down here. Oops, no, B. 2 in the wrong place. 2 plus and YSO4. Okay. So the quickest way to balance this equation is to first you have to decide what is the oxidation state on the elements that are involved. We can assume that oxygen doesn't change. So really the only oxidation states that are going to change are those associated with vanadium and with sulfur. So let's say, what's the oxidation state of vanadium? Well, if oxygen is 2 minus, that means you have 6 minus here, but you have to hold 1 for that. We have to balance 5 minus with a 5 plus. Okay. So that's vanadium on this side. How about vanadium on this side? Well, it's 2 minus for oxygen, but the overall charge is 2 plus. So in order to do that, you've got to balance an excess of minuses. Okay, so let's just check ourselves to see if we're right. If this is 2 minus, then 2 minus and a 4 plus gives you 2 plus left over. So we're good there. Now, how about sulfur? Oxygen again is 2 minus, and we've got 2 of them, so that's 4 minus, and the molecule is neutral. So we have to balance all of these with 1 sulfur. Over here, we've got 2 minus times 4 is 8 minus, and we've got to hold out 2 minuses for the charge, which means 6 minus. That means we need 6 plus there. So now we have all of our oxidation states accounted for. Now, let's see. If we go from this vanadium to that vanadium, are we going to gain or lose electrons? Go from 5 plus to 4 plus, we have gained 1 electron per vanadium. So this is the reduction side. Okay. The oxidation side, and I'll need to make room for that. Because when I use this method, I don't like to put them both lines on either side. I put 1 on the bottom and 1 on the top. So we go from sulfur to sulfur here. If we gained electrons here, we had to lose electrons here, which is in fact what happens. 2 electrons per sulfur are lost per sulfur. Okay. So what's the least common denominator? What's the least number that will balance the electrons? If we want to balance the electrons here, if we need 2 electrons for this one, X needs to be 2. Right? That means 2 vanadium equals 2 electrons. So now the electrons are balanced. And all we need to do is just check ourselves to see if the atoms are still balanced. So let's say that's 6 oxygen plus 2 is 8 oxygen. And that's 2 oxygen plus 4 oxygen is 6 oxygen. So they're not balanced yet. Okay, what does that mean? That means that the vanadium and sulfur are balanced, but the oxygens are not balanced. That's because we did not introduce water and hydrogen ions in the equation. You would have to do that in order to balance the oxygens. But the oxygens are not part of the redox reactions. So it doesn't matter. We can balance them, of course, but it won't change the ratio of vanadium to sulfur. So the ratio of vanadium to sulfur, or X to Y, is 2 to 1. Okay, any questions? Now, if you want to verify what I've done here, go ahead and do the half reactions, balance the entire thing with your water and your hydrogens in acidic solution, and I think you'll find that the ratio still holds. All right. Excuse me. Okay. Now, number 3 is a bona fide balancing equation in acidic solution by the half reaction method. All right, so we'll go ahead and do that one. And then 4 follows up with 1 in basic solution. So we'll get all the mechanics out of the way on the first page. Okay, so if we start off with this reaction, which is a net ionic equation, and balance it in acidic solution. And iodate and nitrogen dioxide. Nitrogen dioxide. There we go. Now we just have to decide first which one's oxidation, which one's reduction. We need to know the oxidation states. I always start with the easiest ones. There are no elements in there, so no zeros, but there is an ion here, and its oxidation state is -1. Then we do the rest of it. So what's the other iodine? This is 2 minus times 3 is 6 minus. Hold 1 out. So we have to balance 5 minuses for this iodine, which means it's 5 plus. So where would it go? It's going from a minus to a plus. So it's obviously an oxidation. It's lost electrons. All right, so we'll do this one, oxidation. And here. And it lost electrons. Right? How many did it lose? Right? It went from a -1 to a 5 plus. I like to do this in 2 steps. When you've got a minus and a plus on either side, how far to 0? Lose 1 to go to 0. And then you lose 5 more to go to 5 plus, which means 6 total. So that's 6 electrons were actually lost in the process. That means the nitrate to nitrogen dioxide would be a reduction. We just need to know what the values are. So that's a 6 minus, 3 times 2 minus, hold 1 out, 5 plus. And if it's a reduction, we have to have electrons to go over here. Now what's this one? Well, let's see, 2 minus times 4 times 2 is 4 minus. It's a neutral molecule, so we have to have all of them balanced by that 1 nitrogen, 4 plus. So if we go from 5 plus to 4 plus, we've only gained 1 electron. 1 electron. You don't have to put a 1 here. So there are half reactions, right? So what do we balance next? We balance everything except oxygen and hydrogen. So we got 1 iodine, 1 iodine, we're done. 1 nitrogen, 1 nitrogen, we're done. Now we balance oxygens with water. We got 3 oxygens on that side. It means we need 3 oxygens on this side as water. Okay. We've got 3 oxygens on that side and 2 on that side, which means we need 1 oxygen on this side. Okay. Now we're in acidic solution, so we balance the hydrogens with protons. So we've got 6 hydrogens on this side. We need 6 hydrogens on that side. We've got 2 hydrogens on this side. We need 2 hydrogens on that side. All right.
Can you hear me okay?
Yes, coming through loud and clear.
Awesome.
All right. We had Kessa for a couple of seconds, but I don't know what happened to her. Maybe she lost the connection. We're currently on number 3.
Okay. Oh, there's a kitty cat.
Yeah, I've got too many helpers in here today. I might eventually have to throw a couple of them out.
Oh.
One of them's asleep. He gets to stay. And another one's minding himself. Tigger wants to be the center of attention right now. Okay, so we've identified an oxidation reaction, a reduction reaction. We've balanced the elements. We balanced oxygen. We balanced hydrogen. Now we need to reconcile the two equations before we can add them together. And you do that by going to the electrons. So we've got 6 electrons here. We need 6 here. Just multiply the whole thing through by 6. That gives you 6 electrons. And then you combine your equations and cancel terms. So we've got, let's put them in this order. So we'll start down here with 6NO3. And then the number of iodines would be 1. Then we have 3 waters. And 6 times 2 is 12 hydrogens. Okay. On this side, we'll put iodate first. Somebody else? Oh, we lost Steffi. She'll be back. And nitrogen dioxides, we only have one of those. And we have how many waters on this side? We have 6 times that is 6 waters. And six hydrogens. Okay. Now we can cancel terms. We can, there's Isaac. We can cancel terms and balance the entire equation, but if you're in the middle of an exam, you just want to answer the question. And the question here is, what's the coefficient for water? So we just need to reconcile the waters. Here we have 3, here we have 6, so the coefficient for water should be 3. And that means the answer is C. Now, if you're the type of person that likes complete answers, just go ahead and cancel terms on either side. Those are gone, that's 6. We can't reduce it any other way, so we have 6 nitrates, 1 iodide, 6 hydrogen, 6 protons, yields 1 iodate, 1 nitrogen dioxide, and 3 waters. So that would be the balanced equation, and the answer to the question, though, is that number 3. I'm check them off as I go so I don't backtrack. So that was acid solution. Number 4 is a problem in basic solution. And unless I miss my guess, it could be. Okay. I did miss my guess. I was looking for one of these equations in here that you work. It doesn't matter what solution it's in, acid or base, because there are no hydrogens and no hydroxyls involved. But this one, it's got water and it's got oxygen on one side, so I think we're probably going to need to do something. The question here is, when the equation is balanced, what's the sum of the coefficients? So we'll start off with our given equation. F2 plus H2O yields oxygen and fluoride ion. Okay. So normally, well, in the past, in the reactions we've looked at up to this point we've had to assume that oxygen was 2- oxidation state and it doesn't change. But in this case, you can see that oxygen does undergo one of those processes, redox. Why? Because this one's 0, and in that molecule, we know it's 2-. So oxygen in this case has undergone oxidation. It's lost 2 electrons per oxygen. So we'll just go ahead and put that one up here. Water yields oxygen, and we went from 2- to 0. This one's easy. That one's 1-, right? Charge on the atom, or the ion. And this one is 0 because it's elemental in its standard state. So that one was reduced. Okay, so now we do elements. Everything except oxygen, so we leave that one alone. This one, we need 2. Here. Now we balance the oxygens with water. We've got an oxygen here and 2 there, so we just need 2 there. Okay. Here, we've got no oxygens to balance. Now we balance the hydrogens with protons, because this is my fake acid method. So we need 4 hydrogens over here. And we're done there. Now we do electrons. So if this is oxidation, electrons end up on the product side. Question is, how many? Well, we've got, let's see, 2 oxygens with 2 electrons each. So we need 4 electrons. And let's see, 2, 4. That's right. On this side, we have to gain electrons. So if it's 1 electron per fluoride, we need 2 of them to balance those. Now what we can do is reconcile the equations. This one needs to be multiplied by 2 to give us 4 electrons. So that means we're going to have 2 here, 4 here, and 4 there. Now we can combine the equations in the acidic version before we change it to the basic. Okay, so we've got 2 fluorines, we've got 2 waters, we've got 4, well, the electrons are going to balance, so we don't need to write that in. And then on this side, we've got 1 oxygen, and we've got 4 fluorides, and 1 hydrogen. Let's see if that's right. 2 here, 2 there, 1 there, 4 there, and 1 there. Okay. Now we can convert it to basic solution. So we have to balance by adding hydroxyls. If we add in a hydroxyl here, it's just 1 of them. So we only need 1 hydroxyl on this side. Okay. So this one becomes 1 water molecule. And that 1 cancels this 1. So we've only got 1 water on that side, plus a hydroxyl, 2 fluorines, 1 water, 1 hydroxyl, yields 1 oxygen, 4 fluorides, and that's it. And that's balanced in basic solution. Now the question was, the sum of the coefficients. So we've got 2 there, 1 there. That's a common mistake. If you see an element or something with no coefficient in front of it, it's always 1. So 2 plus 1 plus 1 plus 1 plus 4. That's it. 4, 5, 6, 7, 8, 9. And let's see. I did something wrong. What did I do wrong? I missed something. Oxidation. Oh, oh my goodness. I didn't balance that one in the first place. 4 hydrogens, 4 hydrogens. So that means the electrons are right. So we need to go back down here. 4 hydrogens with 4 hydroxyls yields 4 waters. We got 2 waters here, so that means those go out. 4 hydroxyls stay on this side. And we've got 2 waters left over. Now let's see. 2 plus 4 plus 1 plus 4 and then 2. So that's 6, 12, 13. There we go. That makes the answer D. Don't make that mistake on the exam. The devil is in the details. Okay, so that's the first page. Let's see if we've already done one like we could do number 5, but that maybe we're going to hold that one because it's just another case of balancing equations in basic solution. 6 is an acidic solution. 7. We can come back to those others if we need to. Seven is just identifying half reactions. Maybe we ought to do that one. That one looks like it might have a glitch in it. Okay. So 7 says, for the redox reaction here, iron 2 plus yields 2 Fe3 plus and 2 chloride. Okay. All right, for the correct half reactions, I'm assuming that what they're looking for is balanced. No, not necessarily balanced half reactions. What half reactions do you start with? All right. So there's the oxidation state for that one. This one's 0. This one's 3 plus, and that one's 1 minus. So which one's oxidized? Oxidation is loss, oil. Iron 2 plus was oxidized to iron 3 plus by losing 1 electron. So if we have 2 Fe, did I write that correctly? Yes. Iron 2 plus goes to iron 3 plus, and it lost 1 electron per iron, which means well, that one can be reduced, right? If we're at a starting point, our starting reaction should be one of these, one of those, and one of those. So that's the simplest whole number ratios for each of those components. Now, why would we want to do that? I mean, this is the balanced equation. Well, if we wanted to put it in some other reaction, that's our starting point, because the coefficients will change for a different reaction. And the other one has to be the reduction. So this one has to gain electrons to yield that, and that's 1 electron per chlorine, which is 2 electrons. So that would be our reduction half reaction. So let's see, that one fits in with Roman numeral 1, okay, and Roman numeral 4. So 1 and 4, which means A. That's the advantage of multiple choice tests. You know what you have to choose from. So in this case, 2 times 2 times 2 is not an option, right? So that eliminates that possibility of making that mistake. If I were evil, I would have put both of those in the selection, and then probably got some arguments from my students. But in this case, that's the best answer, right? like I say with all my multiple choice questions, if you can't find the right answer, give me the best answer. Okay, that was 7. Let me mark that one in case I backtrack. Okay. Let's see, 8. 8 is really simple. How many electrons are transferred? That won't take much time. Let's do number 8. So I'm guessing since you've got protons and waters in this equation, that this one's balanced. We can verify it. 2 chlorates, 12 protons, 10 iodides yields 5 iodines, 1 chlorine, and 6 waters. Okay, so let's see. 2 chlorines, yep. 6 oxygens, 12 hydrogens, 10 iodines. Okay, so it is balanced. But the question is, how many electrons are transferred in this process? So rather than bust it up into oxidation reduction, you can do the oxidation reduction on that balanced equation, just like we did earlier with the second one, I think, so number 2. What you have to do is decide which are the oxidized elements and which are the reduced elements. So if this one's 0 and that one's definitely an ion, we need to say 3 times 2 is 6 minus. We need to hold one out for 5 minus. There we go. So this is 5 plus, and hydrogens and oxygens in this case don't change. So iodine must be the one that changes. I left out a charge, I think. Yep, that's the charge. So -1, 0 means we had to lose electrons here. All right. I should have spread it out, but I'm going to try to do this without too much confusion. I'll put it down here. If chlorine is going to from 5 plus to 0, that means we had to add electrons to it. So chlorine 5 plus, and I'm just going to write the chlorine part, to chlorine 0. I will write 5 now. We have 5 of them. And 2 up here, so we had to add 5 electrons per, but we've got 2 chlorine, so that means 10 electrons. So let's see if that works. It's 2. So 2 times 5 plus is 10 plus, and 10 plus 10 minus is 0. So we're good. So 10 electrons were transferred here. Now, if the equation is in fact balanced, that's our answer. But to verify it, we should go and look at 10 iodines, or 10 iodide ions, and leads to here zeros. So that means we have to add so many electrons. Well, 10 minuses to a 0 is 10 electrons. And that would be right because we have 10 iodines here. So that's it. 10 electrons were transferred in the process. Now, why would we need to know that? Well, if you're going to split that into an electrochemical cell or galvanic cell, you need to know how many electrons are transferred if you want to calculate the true electromotive force. Not this one, but this one. By the Nernst equation, you need to know how many electrons are transferred in order to use the equation. Log Q. So you need that N, number of moles of electrons transferred. Say that was 8. All right, let's see. We don't want to spend too much time on the floor, of course. 8. Let's see. Okay, number 11. That's the first one that we encounter where we're actually calculating the standard voltage or electromotive force for this reaction. All right. Okay. 11. Consider the galvanic cell that uses this reaction. E2 plus dichromate ion, Fe3 plus, and chromium. Okay? So what we have to do is decide which one's the cathode and which one's the anode. Cathode is reduction, the site of reduction, and the anode is the site of oxidation. So let's see. That's a 2 plus oxidation state, 3 plus, 3 plus. We just need to calculate this one. So 7 times 2 minus is 14 minus. And 2 minuses hold out 2 minuses for the charge. So we have to balance 12 minuses with 2 chromiums. So that means each one has to be a 6 plus. There we go. Now we have our oxidation states. Iron goes from a 2 plus to a 3 plus, which means oxidized. Right? So it's oxidized, which means that's the anode. And we go from Fe2 plus to Fe3 plus and 1 electron. Reduction would be the site, would be the cathode. So that would be dichromate. There's only one left, so it has to be that one. So it went from 6 plus reduction, so we have to have electrons, and it went to 3 plus. Okay, so we don't have to do this, but it's just bugs me if they're not balanced. So we're going from 6 plus to 3 plus would be 3 electrons per chromium, which means 6 electrons, right? So this would be did I say that right? If this chromium is 6 plus and it goes to 3 plus, it has to gain 3 electrons per chromium, 6 electrons. Okay. So go back to the question. Calculate the voltage for the standard cell. That means this one. Standard conditions. So in this case, all you need to do is identify the anode and cathode, and you can use the formula if you want, which would be what? The electric potential for the cathode minus the potential for the anode. Now, why do we write them that way? Because all potentials that are given in the table, like, oh, wrong page. Here we go. Like in that table right there, those are all reduction potentials. They're always reduction potentials. This one's okay. It is a reduction. But that one's an oxidation, so you have to change its sign, don't you? So what's the reduction potential for the cathode? Dichromate to chromium 3 plus. Okay, so we look, dichromate to chromium 3 plus. Looks like it's 1.33 volts. Let me check myself. Be sure. Yes. 1.33. And then minus the one for the anode. So this one would be, if you're looking up the voltage, you go from this to that, right? Because it's a reduction. You go Fe3 plus to Fe2 plus. So we look up that one, Fe3 plus to Fe2 plus. That's not it. Let's go down. That's not it. Go back over here. Here it is. Fe3 plus, 1 electron, Fe2 plus, 0.77. Okay? So we just subtract that one from the other one, and we get 0.56. Oh. Okay. I chose to work the problem with this equation, but when we went through the lecture part, I didn't even refer to that equation. I just said, how would you flip one or the other to give you a positive voltage? So if we said that this one had a voltage of 1.33, and this one had a voltage, the reduction side, of 0.77 volts, how would you arrange those so that you get a positive value? Well, if you flip this one, you get a negative that's too big. That's the wrong direction. So you need to flip that one. So that makes this one the anode, because you have to flip a reduction to an oxidation, which makes it the anode. So that's the other logic that you could follow. If you prefer equations, that's fine. You just have to identify which one's the cathode and which one's the anode. And if you have a balanced equation, it's no problem. But if you're presented with independent equations and nothing's balanced yet, they've not been combined, then it may be better to use the logical procedure rather than the equation. So you have those two methods in your bag of tricks to use if you want. Okay, that was 11. Let's see. And that would make it D. Yeah, D. A positive 0.56 volts, which means that as written, this is a spontaneous reaction. Which also means what about the delta G, Gibbs free energy? Whatever value it is, it'll be negative. Okay. And that was 11. Okay. That's definitional. This might be worth looking at. Number 14. Okay, we're given the we're given the galvanic cell, and it might be valuable to draw it. So for 14, for 14, let's see, we normally put the anode on the left, and the cathode on the right. So this would be copper, here, and silver here, and they're connected. With a voltmeter, okay, which means if this is the anode, oxidation means we're producing electrons as products, which means they're going into the wire. Over to the silver. And we've got copper, 2+ ions in solution, and here we have silver, 1+ ions in solution. And we also have a salt bridge. Okay, salt bridge. We're also told something else about the solutions. We're given our spectators. For the balanced electrochemical cell equation, spectators don't matter. But to answer the question, we need to take the spectators into account. And on this side, we have copper nitrate, okay, nitrate ions. And on this side, we have silver nitrate. Okay? I guess we'd have 2 of these here, wouldn't we, to balance it. Okay. So we are looking for which statement is false. We know that this is the anode, this is the cathode. Let's see if that's true. The reduction potential for this reaction is positive 0.8, and the reduction potential for this one is positive 0.34. So that's right. You would have to flip this one to a negative, and the negative added to the 0.8 would then be 4.6 plus 4 plus 0.46 volts. And that's true because the conditions are standard, 1 molar solutions. Okay, so which one's false? Let's see, test taking technique. Are there any here that say 2 of the above, none of the above, all of the above? No. So we only have to find the one that's false, and when we find it, we can stop. So how about A? Electrons flow in the external circuit from the copper electrode to the silver electrode. That's true. So A is true. How about B? The silver electrode increases in mass as the cell operates. Well, let's see what's happening. The silver electrode is on the cathode side, which means silver plus ions are being reduced. Yes, reduced. Electrons added to silver makes more silver metal, which is true, makes the silver electrode increase in mass. And that's true for all cathodes. If you have an active participant in the electrode itself, then it will gain mass. If the electrode does not participate in the reaction, then that question is moot. It doesn't work. If you have to use a carbon electrode or a platinum electrode, because the reaction is taking place in solution totally, producing no solids at all, at least no solid on the electrode, then, well, I'll take that back. There are some cases where you can precipitate a solid on your platinum electrode. So, but in this case, let's answer the question. The silver electrode increases in mass. That's true. How about C? There is a net general movement of silver ions through the salt bridge to the copper half cell. Well, the part of the question, or the part of the statement that is true, is that there is a net movement of ions, right? In order to balance charges, because we're moving negative charges over here, that means we have to move positive charges over here to balance them. But silver is not the one that's moving, because it's being reduced into silver metal. So it doesn't move that way. It's consumed. So what we would have is a net movement of copper ions over to the other side. Now, eventually, that's going to interfere with the reaction, but in the beginning, no, it's fine. That means C is false. So we found our answer. Let's see if D and E would lend anything to the conversation. You know what? I may have misspoke. Instead of the copper ions moving, all we have to do is balance the charge. So if negative ions are moving over here, we'll keep the negative ions moving that direction. Right? It's kind of like a circuit. Electrons are moving. And if we want the electrical charge to move negative all the way around, all the way around, all the way around, keep doing that, then the one that moves is the nitrate. Nitrate moves into the salt bridge and over. And the positive ions stay put. So what's happening? We're decreasing the concentration of silver ions over here, increasing the concentration of copper ions over here. And how long will that continue? Till we reach equilibrium. When equilibrium is reached, the battery is dead. Okay, that was D, which is true. And then E, some positive copper ions pass through the salt bridge from the copper half cell to the silver half cell. Well, technically speaking, that's true. But there's not much of that happening. And it's designed that way. And the way you do that is you put a barrier in between. That's why these salt bridges are always filled with a gel of some kind to slow the movement. Okay, but E is true. And it can be measured. Okay, that was 14. Let's see. Oh, let's do 15. That's a good question. Let's see, gotta hold it steady while I wipe. Okay. 15. Oops. 15. Which of the following species cannot function as an oxidizing agent? So let's write our choices up here. Okay, dichromate, 7. And D is iodine, iodide, okay? And manganate. Oops. Okay. Cannot function as an oxidizing agent. What happens to the agent if it is an oxidizing agent? If it causes oxidation in something else, it has to be reduced. Right? So they need to be reduced in order to be oxidizing agents. Since we have no choices that are one of the above, two of the above, none of the above, we just need to find one. Which one cannot function as an oxidizing agent? It's the one that cannot reduce, cannot be reduced further, or resists. I say cannot. You can always force something to do something else, but it won't spontaneously be reduced. That makes it an oxidizing agent. Right. So, can sulfur be reduced? Well, yeah. Right. You can add electrons and make sulfide ions, or you can. Well, that's the best example. So it could go to something like, I don't know, something like that. That's valid, right? It's in the same family as oxygen, so 2 minus would be the most likely choice. How about this one? Can the nitrogen be reduced? Well, let's see, what is it now? 6 minus 5 plus. Oh yeah. And you can look at your periodic table that's given and look for nitrogen. Nitrogen can be anything from -3 to +5. So yeah, it could go to almost anything. No examples there. How about chromate? So this is, what was it, 6 plus before, wasn't it? Yeah, 6 plus. So the other most common ion for chromium is chromium 3 plus. So that means it has to be reduced. I think that's the dangerous one. How about this one? What would happen to this one if it were reduced? It would have to gain negative charge, right? Iodine's not going to do it. Halogens like -1, and that's all they want, right? Because -1 means a complete valence shell. So that one will not be reduced. Manganese, yeah, it can be reduced further. So this is our answer. That's the one that will not function as an oxidizing agent because it cannot be reduced. Cannot, in quotes. Okay. Let's see. Ooh, 16's a good one. All right. 16. Which metal, aluminum or nickel, could reduce zinc 2 plus to zinc metal if placed in a zinc 2 plus aqueous solution? So we just have to compare zinc with the other two and see which will produce a spontaneous reaction. Right? So we're given the reduction potentials for each of these at minus 0.76 volts. Aluminum, 3 plus. Okay, at minus 1.66 volts, and nickel at minus 0.23 volts. Okay, the question is, which metal could reduce zinc 2 plus? So which one of these, if this is the cathode, which one of these could be an anode? So if these can reduce that, that means they would have to be oxidized. That means the charge would have to be, the voltage would have to be reversed, right? So if we take minus 0.76 and plus 1.66, we get a positive value, right? So aluminum can do it. How about this one? This one would be 0.23 and minus 0.76. That's negative. Nickel cannot do it because nickel as an anode will not produce a spontaneous reaction with zinc 2 plus ion. Okay, so that's, well, actually, it's that metal, which makes it A. Okay? All right, let me check that one off. And I better get a move on it because I'm trying to hit the concepts.
Dr. Bly,
Yes.
I have a doctor's appointment. May I go and then just watch the rest of the lecture?
Oh, sure.
Okay.
Before you go, I was talking to Steffi earlier. I think what we're going to do on Thursday, since that's the exam day for chapter 18, normally what I do is introduce a new topic, where there are no new topics. Okay?
Right.
So I may, on that day, start introducing topics for final exam review.
Okay.
And then we can continue that on the following Tuesday. That way you kind of have more time to reabsorb or refresh your memory on stuff for the final exam.
Okay. Perfect. All right. Thank you.
See you later. I'm going to take a short break, bathroom break. So I'm going to pause it, and I just hope I remember to restart it. The recording. Let's see, that one's about used up. Let's get a fresh one here. All right, let's see, where was I? That was 16. I was looking at 17. I don't think 17 is going to add anything to the conversation. That's a standard potential. Um, 18, 17, 18, 19. How about 20? Okay, 20. What's the value of Q? Okay, that would be valuable. Something new to add to our quiver. Okay. We want to know what Q is for that reaction. We're given the half cells, and if we need to calculate Q for this reaction, we need to have a balanced equation. And that'll take some doing, right? Because Q is just the non-equilibrium value for K. All right. Before we do that, let's see, we only got 45 minutes left. Let me sneak ahead and be sure that okay. Okay, that's nothing new. Okay. Keep this one in reserve. Come back to that one. Let me work from the back forwards. Okay. I think the only thing we haven't covered yet is equivalence of G and the electrolytic cell. Okay, so I think we've got time to do this, what did I say, 20? We got time to do 20. Let's get that one out. And I think we use that information in subsequent questions also. Yeah, 20 and 22. So we'll do 20, then we can move to 22 and calculate the true voltage of the cell. All right, so in order to answer 20, do the Q, we need a balanced equation. And I think what I better do is make a lot of room. So this is going to be 20. Here we go. Now the cell, let's confirm with the half reactions that are given whether or not the cell is written as anode left, cathode right. So let's look. If we take chromium as is, which would be the right-hand side, normally cathode, reduction potential, and we make the manganese side negative, that will give us a negative total. So this cell is actually written backwards. The manganese side should be on the right-hand side. It should be the cathode. So that means reduction is this half reaction. Okay? And oxidation is the other side, because that half reaction would have to be reversed, making it negative, added together with manganese to give you a positive potential. Okay, just a second. Yeah, I'm just checking myself. I'm on the right track. So the oxidation reaction would be flipped. Chromium would be flipped, which would put this one on that side, like that. And then this one, 7, 14 hydrogens, plus 6 electrons. Okay, so that's the way we would write the anode, cathode. Okay, now we have to combine these equations in order to calculate Q. And we probably, in order to answer number 22, we also need to tally the number of electrons transferred. Here we've got 5 electrons, there we've got 6 electrons. Let's just do a quick tally here, quick check. 1 manganese, 8 hydrogens, 4 oxygens, that's good. How about 5 electrons? Is that right? This is 8 minus 7 plus 5 electrons, yes. Okay. Second, deter a cat. He's been getting ready to dig his way into the bag of kitten caboodles. I keep him in the office so the other cats don't dig into him before I'm ready to serve. Might have to throw him out. Okay, this one. This chromium is 6 plus. We did that earlier. 3 plus. So we're going to go 3 plus to 6 plus is 3 electrons per, means 6 electrons, 14 hydrogens, 7 oxygens. We're good. Okay, now we can balance. We just need to make 6 and 5 jive. Okay, what do we do when one of them won't divide into the other, or they're not even, or they're not both odd and divisible? You cross multiply. So that means this one has to be multiplied by 5. This one has to be multiplied by 6. So in order to do that, we have 6 manganese, or manganate, and 10 chromium. Okay? And then we have 48 hydrogens and 35 waters. Okay? Then on the other side, we have 6 manganese 2 plus ions. We have 5 dichromates. We have, hydrogens. We have 5 times 14 is 70 hydrogens. And 24 waters. Now what's N? How many electrons were transferred? 30. 30 electrons. Okay, can we reduce this any further? Well, let's see. Let's cancel some things first. Hydrogens. 48 of those are gone, and that leaves 22 here. Right? 22 plus 48 should be 70. That's right. Waters. Those waters are gone, So 24 from that is 11, right? 11. Anything else? Well, let's see. 610, 65. Can't reduce it any further. So what we have is 6. This is the balanced equation. Manganate, 10, 3 plus, 11, water, 6, Mn2 plus, and 5, Cr2O7 minus plus 22, H plus. So there's our balanced equation. Now, to calculate the Q from that, I'm going to have to erase all this. And start compiling the Q. Right? So we have this one on the numerator, Mn2 plus to the 6th power. Then dichromate to the 5th power. And then hydrogen ions to the 22nd power. Okay? These are all in solution, so we have to consider them. We have to hang on to them. In the denominator, we have manganate to the 6th power, and we have chromium 3 plus to the 10th power, and water, which is a pure liquid, doesn't count. Right. So that's our expression for the Q value. And let me just check my work here for a second. Yeah. Okay. So now you go to the drawing and you find out what those concentrations were. Right. Manganese 2 plus, Q, 0.2 to the 6th power. Dichromate is 0.3 to the 5th power, 0.01 to the 22nd power, wait a minute, that's not right. Mn2 plus is 0.2, dichromate is 0.3. Oh, that's right, sorry. Don't panic yet. The manganate ion is 0.1 to the 6th power. And the chromium 3 plus is 0.4 to the 10th power. Okay? All right. Now, 20. Here we go. So if we resolve all those values, we should end up with Q equal to 1.5 times 10 to the minus 41. Okay? And that's B. Now we've got this one here, along with that one. So let's go to 22. And it should be a simple calculation now. 22. So the question for 22 is, what's the cell potential at 25 degrees? 25 degrees is that place where we can use the modified Nernst equation. We need the standard potential, which we don't have yet. And then we subtract 0.0591 over n times the log Q. So we need the standard potential. Well, if we go to the standard potentials that were given before, chromate becomes negative, the chromium side becomes negative. So standard potential here is 1.506 minus 1.330. 6, 7, and 1. 0.176 volts. So that goes in here. Then we subtract 0.0591 divided by 30 electrons. Yep. And then we take the log of the Q value. There we go. And that will give us E. So if we do all that, take the log of that, and then times this, divided by that, subtract it from this, what do we get? Well, in the interest of time, this will actually be a positive value and add to the voltage of 0.256. So the conditions that we set up in our galvanic cell actually increase the voltage from the standard. Now, if Q were equal to 1, then this whole term would be 0, and E would be equal to that. So it would take some doing, but you could set this Q up so that it would resolve to 1. But actually, the easiest way to do it is make 1, 1, 1, 1, 1. And then Q has to be 1. Those are standard conditions, right? Yeah, those are standard conditions. Okay, so that's 22. 20 and 22. Here we go. All right. Now, I was holding which one? 30. All right. So I think we've got time to do 30 and then one of the electrolytic problems, which is just galvanic in reverse. Here we go. Dropping everything. Okay. 30. Actually, 30 won't take very long. Right, following has a potential of 0.92 volts. So this reaction has a potential of 0.92 volts. 2 Hg2 plus and hydrogen gas yields 2 hydrogen plus aqueous plus Hg2 plus. Okay, so which one's reduced and which one is oxidized? Well, this one is 2 plus charge. But here we have 2 of them with a 2 plus, and that's the way mercury works. You never have a single mercury alone with a 1 plus charge. You always have 2 of them together with a 2 plus, which means this is a 1 plus charge or oxidation state for mercury, because 2 of them have to divide 2 plus. This one is 0, and this one is 1 plus. So we have reduced this one by adding electrons to make this one. And 1 electron for each, so that means we need 2 of these. And 2 of these. There we go. So that's the reduction. And the oxidation occurs with this one to yield that. Plus 2 electrons. Okay, and the voltage for this whole reaction is 0.92. So it means it's spontaneous. And the question is, if the concentration of ions is 1 molar and the pressure is 1 atmosphere, so this is 1 atmosphere, this concentration is 1 molar, and this is 1 molar, and this is 1 molar. You get that voltage. Then the question is, what is the voltage for that half reaction? Okay, it's kind of a trick question. This is the standard hydrogen electrode. All voltages for reductions are compared to that half reaction. So this one is by definition 0 volts. That means that this half reaction is 0.92 volts. Okay? Kind of tricky. All right. Now, let's see. So, all right, we got time for 44. All right, 44. An excess of finely divided iron is stirred up in a solution that contains copper 2 plus. So we've got iron finally divided, and copper 2 plus solution. Okay. And what do we produce? Well, we do get some, we have some of this left over, and we get some of this, right? So what happens to that one? Well, it produces some ion, probably 3 plus. It's my guess. You don't need to know that to answer the question, because the conditions are set up, and here's the key. The system is allowed to come to equilibrium. And then the question is, what potential then develops between the electrodes? We're at equilibrium. Zero volts. The actual is 0 volts. Now, there would be a standard potential, of course. But at equilibrium, the question is, what's the voltage on the cell? 0 volts. Another trick question. Okay, now let's get to an electrolytic cell and do one of those calculations. And let's see. If we have time, we'll come back to that one. Well, where did it go? I know there's one in here. And we could do this one, but that's incomplete. I want one that has a final answer. How about 64? This is a very practical problem. If you're running a garage with electroplating functions on the side to make a little extra cash, you got antique cars coming in, and one of them needs its bumper replated in chromium. So your excuse me, 64. Your solution is this CR2 SO4 3, and you're going to produce this on the bumper. And the question is, if you run a current through that solution, actually through the bumper, and the bumper serves as the cathode, because the site of reduction will take this, which is what? That's a 2 minus, so that's 6 minus 3 plus. So that's a 3 plus chromium to 0. That means you need to add 6 electrons. Now, I left out the sulfate because it's a spectator. But going from this one to that one requires 6 electrons for every 2 moles of chromium, or 3 electrons for every 1 mole of chromium. That's an important ratio. So now let's go back to the conditions. We're running a current of 11 amps for 145 minutes. Okay. So what does amp mean? An amp means coulombs per second. 11 coulombs per second are going through that bumper. And those electrons that are being supplied, or that charge, is reducing this chromium to that solid chromium on the surface. Okay, so what's the mass of chromium that's deposited on that bumper in this amount of time? We want to start with that value and end up with mass. So it's a dimensional analysis problem. All right, so let's see. Let's start off here. 11 coulombs per second. So how long is it going to be running? Well, 145 minutes. Right? But that's not seconds, right? So we got to convert it to seconds. 60 seconds per minute. There we go. So we got that term canceled out. That one canceled. And now we're down to the total amount of charge that is supplied in that amount of time. That's charge. That's not moles of electrons. So we need a conversion from charge, or coulombs, to moles of electrons, which is, I never had this one memorized. Let's see, 64. It's in the useful information. 90-something thousand. 96,485. So 96,485 coulombs is per mole of electrons. So now we have moles of electrons. We have a conversion factor that will take us from moles of electrons to moles of chromium. So we need moles of electrons to moles of chromium metal. So for every 6 moles of electrons, you get 2 moles of chromium. We can do it that way. Or 3 to 1, same thing. So that takes care of moles of electrons. Now we've got moles. Now we're converting to mass. You just need molar mass of chromium, right? Now we've analyzed our dimensions all the way down to there. We just need a value for chromium, which is 51,996. 996. There. I'm going to do this one rather than reading it off. Got a few more minutes. Okay. So now how do you calculate this? Well, the most efficient way is to take everything in the numerator times, and then everything in the denominator divide. So I'm going to say 11. Let's go 11. Oops. 11. This is in the numerator. Times. That's in the numerator. Times. This is in the numerator. And that's in the numerator. Okay. Now divide. 96,485. And 6. And 1. So I get 17.2 grams. Now, did I get anywhere close to the answer? Yeah, that's E. Okay, so those types of problems are dimensional analysis. But in order to do the dimensions correctly, you need this balanced expression. You've got to make the transition between moles of electrons to moles of product. That's the key to this problem. Okay, let's see. Yeah, 56, nothing special. 56 is buried in this one. Let me see if there's anything else. Got a few more minutes. Anything else that would be helpful? That we haven't covered. We're good. Now we haven't actually done a concentration cell calculation. So if we were to do a concentration cell, let me see if I can come up with something. Maybe I can, and maybe I can't. In short order. You got 5 minutes. I don't want to keep you in here any longer than I have to. Okay, here's one. So let's take this one. I'm going to use line notation, right, to describe this cell. So we've got that one, that one, and the concentration here is 0.816 molar. That's aqueous solution. And then our salt bridge. And on this side, this is the anode. So we're going from this one is being oxidized to that one. And on the cathode side, this one is being reduced to that one. But the concentration on this side is 0.843 molar. Okay? Let's see. And the standard potential, reduction potential for this one, plus 2 electrons yields copper solid. And the standard is 0.34. Okay. Now, when you have a setup like this, and we're going to use the Nernst equation, minus times log of Q. So in order for this to be Q, these have to be different concentrations. If they're the same concentration, then the cell will not operate. They have to be different concentrations. The trick is to decide which one goes where, because that's a solid and that's a solid. They don't enter into the Q calculation. So the Q in this case would be the anode divided by the cathode. So we would have 0.816 divided by 0.843. What would happen, just hypothetical, if that concentration were over here and this one were over there? The voltage, the electrons would move in the other direction, right? They wouldn't move from this side to that side. They'd move from this side to that side. And this would be the anode, and that would be the cathode. Okay? Just saying. Okay, so we've got this voltage here, 0.34. Now we need to know how many electrons are transferred, right? This is really simple. If you're going to go from 2 plus copper to 0 oxidation state, 2 moles of electrons. So that goes there. So this one minus this term, well, minus this term times that term is equal to that. So let's say, what's our Q? 0.816, 0.843 divided, we'll take the log, and then times 0.0591, divide by 2, and then change the sign, and we have 4.18 times 10 to the minus 4 volts. Our answers are given in, well, one of them is volts and the rest are millivolts. But the one that's given in volts is the wrong number. So we need to change to millivolts, right? So this is a positive. A millivolt would be what? 10 to the minus third. So this would be 4.18 times 10 to the minus 1 millivolts. Or in standard notation would be 0.418 millivolts. Okay? Plus value, which means, as written, the cell will produce a charge, an electromotive force of 0.18 millivolts in that direction. Now, what are some clues? If you happen to put your numbers in the wrong place here, what will happen? You'll end up with a negative voltage. And as written, you know it's wrong because it should be a positive voltage. If this side's lower concentration than that side, it should go that way. Okay, and we discussed that in class in terms of Le Chatelier's principle. What you want to do is, if this is the smaller value, you need to increase this one and decrease that one. And in order to decrease this one, you have to make copper out of it. Right? So that means it has to be reduced. So that's a key there, that this is the reduction side and that's the oxidation side. Once these concentrations are equivalent, the cell's dead at equilibrium. Now, what did we not cover? Oh, we didn't cover delta G, and we're out of time. Right. So if you have to go, if anybody has to go, I'm going to find one that talks about delta G and be sure it's in the recording. All right, let's see. Close quarters, knocking thing on the floor. Again. All right, 7. Okay. All right. So let me see if I can find one that incorporates delta G in the process. Okay, got a work function. I think that would be more valuable anyway. So let's do this one. Pick that up again. And let me give you the conditions. So we're going to need this information. So we need copper 2 plus 2 electrons yields copper, and that's 0.342 volts, and that's standard. Okay, and then we got this one, lead 2 plus 2 electrons yields lead, and its voltage is minus 0.130 volts. Okay. For a galvanic cell, using these coupled reactions, so that means when we say galvanic cell, it has to be spontaneous in production of a voltage. Right? It's not the electrolytic, it's the galvanic. So we need an arrangement of these reactions that will give us a positive voltage. If we make that one negative, we get a negative voltage. If we make this one positive by flipping that reaction, then we get a positive voltage. So we would say this one would be the cathode, where reduction takes place. At 0.342 volts. And this one is the anode, so it has to be reversed at 0.130 volts, positive. Add those together, and we get a total of 0.472 volts. All right. So here's the question that you need to answer. What's the maximum amount of work that would be accomplished with this reaction in terms of 1 mole of lead? So if 1 mole of lead goes from here to here, what's the maximum amount of work? Well, what function do we have that equates work with electrical potential? We have this one. Here we go. That should be in your useful information. Let me just check to be sure. Work. There's one work. It's not the right work. We need a different work. Let's see. I don't see it. All right. That's an oversight. Okay. So it's okay for you to write this one down on a card and bring it to the exam, because I don't see it. All right, we sort of have it there. We have this one. G is equal to minus N Faraday's E. The maximum amount of work that can be obtained from a process is equal to the negative, as equal to delta G. Right. So this is actually that, and this term is equal to Q, the charge. Okay. So all that being said, this equates to minus charge times the electrical potential, the maximum electrical potential. Okay. So what we have to do is determine what is this value. Right? And remember that voltage is equal to joules per coulomb. Right? That's an equivalence. Joules per coulomb is volts. We need that because if you insert this voltage in here and you just put it in as volts, nothing cancels out of charge. But charge in coulombs will cancel that part and leave you with joules, which is the unit of measure for work. Okay? So this value here is also 0.472 joules per coulomb. What we need to determine now is how many coulombs are represented by 1 mole of lead. All right. So let me make some more room. We don't need that anymore. So 1 mole of lead is produced for every 2 moles of electrons. Okay, that's our conversion. Which just means that if we're saying that 1 mole of lead is converted, we're actually transferring 2 moles of electrons. So for 2 moles of electrons, what will that be in terms of coulombs? 96,485, I think. Yeah, coulombs per mole of electrons. Okay, there. So now we have twice that, which would be, let's see if I can do it in my head. 0, 17, 9, 12, 19. 192,970. Let's see if that adds up. Yes. So that's coulombs. For 1 mole of lead, that's how many coulombs, that's the charge amount that's required. So now we have this voltage in terms of joules per coulomb, and that charge in terms of coulombs. So if we multiply this one together and that one, coulombs cancel and we get joules. So if we multiply those two together, we get minus, because of that sign, minus 9.108 times 10 to the 4th joules. Okay? So just for argument's sake, let's say that's a pretty big number. Let's put it in terms of kilojoules and in standard notation. So kilojoules would be 10 to the minus first kilojoules, right? 10 to the minus first kilojoules. Or in standard notation, that would be minus 91.08 kilojoules. Okay? What that means is this reaction releases energy in that amount because it's a negative sign. Remember, it's leaving the system, so it's a negative sign. And that energy now is available for doing useful work. That's the maximum amount. So you won't get all of that out. I mean, some of it will be lost in various forms. One of them at least in terms of entropy. All right. So that we've introduced the terms of what's work and how do we equate work to voltage. Let's see. That's probably covering all our bases for electrochemistry. All right, so I'm going to call it a day for chapter 18 in Zoomdal on electrochemistry. And officially, the exam date is next Thursday. And just a reminder, next Thursday, instead of introducing a new topic, which is normally what I would do, since there are no new topics, we'll start talking about the final exam. And we'll use next Thursday and the following Tuesday to discuss things in the final exam. And then you can actually take the final exam whenever you want. I mean, if you feel confident, you can take it now. But I will give you till a week from Thursday to take the final exam. And also a reminder, the final exam is derived from a standardized American Chemical Society test. So the questions will be in multiple choice format, but they will not be, you can't go back to earlier exams and derive them from that. You need to know the concepts and know the procedures that are required to answer questions in order to pass the final. And I think the final is worth, let's see, just as a reminder, the final is worth 20% of the grade. So you need to do pretty well on it. And if you do pretty well and you need some boost in your grade, that's a good place to get it. All right. So we're done for today. See you next Thursday.